Assalamu alaikum everybody. I hope you are all fine and staying at home. As you know, due to the current circumstances, we have shifted to online learning and teaching. Therefore, this is our first online lecture on digital signal processing, and this is actually the fourth lecture on DSP. First three lectures we already discussed in the classroom. We have so far discussed about the introduction of the course, and we have discussed type of signals, and also we have discussed type of systems. Now we are going to discuss the analog and digital conversion process. This is the first thing that you do in digital signal processing. You convert analog signal into the digital form. You probably already familiar with the conversion steps, but obviously we are going to get more insight on this topic. As you all know, all the signals that exist naturally are analog signals. They come from sensors, transducers, or by any other means. Like our speech signal, acoustic signal, they are all analog in form. In order to process them on a digital computer, we must digitize them using analog to digital converter. The first step that you do is sample the continuous time signal into the discrete intervals. So x of at is a continuous time signal, for example. Then it would be converted into the sampled version and would be represented as x of n. So t is the independent variable in continuous time signals, and n is the independent variable in discrete time signal. T can have any value, however n is always integer. That is the condition that differentiates discrete time signal from continuous time signal. Once the signal is sampled, then it is quantized. It means the discrete time signal still have continuous amplitude. That continuous amplitude is now converted into the discrete amplitude using quantizer, and then each discrete amplitude is assigned a different code using a coder, and in that way you can convert continuous time signal into discrete signal using this three-step process. Now we are going to discuss each step individually. The first one, the sampling, is very complicated process, and we have to choose the sampling rate and the sampling interval very wisely, otherwise we are going to miss the information. So we will spend more time on sampling and quantization, and coding is simply assigning a digital code. The continuous time signals are converted into discrete time by taking samples of continuous time signal at discrete intervals of time. If x of at is the continuous time signal and it is applied at the input of the sampler, then output of the sampler would be a discrete version, which is xa of n. This is how the discrete signal is represented in most of the textbooks, and this you already know is the continuous time signal, where t here is the sampling interval. It defines how far the samples are spaced from each other. Obviously, if the samples are closer to each other, the reconstruction of the signal would be much easier and accurate. For example, this is a continuous time signal, and it is sampled at the rate 1 second. Here the capital T is equal to 1 second. It means each sample is spaced 1 second apart. So you can obviously see from this figure that we cannot reconstruct sine wave accurately from this sequence. However, if we decrease the sample space or decrease the sampling interval, for example here, now we have 10 samples in 1 second, and you can see now it's very easy to reconstruct the sine wave from these samples, and if we increase it further, you can see it accurately looks like a sine wave. There are many ways to convert continuous time signal or the analog signal into the discrete time signal. For example, using uniform sampling, which is also called periodic sampling, or non-uniform sampling. The Uniform sampling is mostly used in practices, and it is described by this relationship. You can see xa of n, which is the discrete time version of the continuous time signal, is equal to xa n into t, where this t is the sampling interval and it is constant in uniform sampling throughout the time interval. In non-uniform sampling, however, t may vary. For example, from minus infinity to 0, t is something else, and from 0 to infinity, t is something else. But in uniform and periodic sampling, the t, the sampling interval, is constant from minus infinity to infinity. Now we can think of a sampler as an ideal switch which turns on momentarily after each t seconds. When a continuous time signal or the analog signal is applied at the input of the sampler, then this sampled sequence is produced. Each sample is spaced t seconds apart. The reciprocal of t is. In periodic sampling, there exists a linear relationship between the time variables of the continuous time and discrete time signals, as shown in this equation. Or alternatively, we can represent this in this form, where capital T is replaced by 1 upon Fs. Now, since the time variables are linearly related, it means there would be some relationship in the frequency variables as well. So let's say the frequency variables of continuous time signal are capital F and capital omega, where capital F is the cyclic frequency and omega is the radial frequency of continuous time signal. And similarly, small f and small omega are the frequency variables of discrete time signals, where small f is the cyclic frequency and small omega is the radial frequency of discrete time signals. Now, in order to establish the relationship between the discrete time and continuous time frequency variables, let us consider a continuous time sinusoidal waveform as shown in this equation 1, where A is the amplitude and capital F is the cyclic frequency of this. Now, if we sample this continuous time signal using uniform sampling, then T would be replaced by NT or N upon Fs. So let us, after the substitution, we'll get this mathematical expression: xa nt equal to a cos 2 pi f nt plus theta. Or if we replace t by n upon fs, we will get this equation. Now let us compare equation 1 and equation 2. We'll get this relationship: small f would be equal to capital F upon fs. So this is the relationship between the frequency of discrete time signal and frequency of continuous time signal. Same relationship can be established for radial frequency as well. Here the small f is called relative or normalized frequency. The range of frequency variables of a continuous time signal can be from minus infinity to infinity, which means f and omega can have any value from minus infinity to infinity. However, in discrete time signal, the range of omega can be from minus pi to pi. If the signals are sampled outside this range, then aliasing effect occurs. In terms of cyclic frequency, it is from minus 1 upon 2 to 1 upon 2. Therefore, the fundamental difference between the frequency variables of continuous time and discrete time signal is their range of frequencies. And we must keep in mind that the discrete time signals can have the frequency range from minus pi to pi, or minus 1 upon 2 to 1 upon 2. So in periodic sampling, basically we map infinite frequency range of variables of a continuous time signal into the finite frequency variable range, which is summarized in this table. Here you can see this is the continuous time signal frequencies variables and their ranges, and on the right hand side we have discrete time signal frequency variables, their units and their frequency ranges that we discussed in the. Relationship between the Ct and Dt frequency variables is shown in following figure. The horizontal axis of this figure represents the continuous time frequency and the vertical axis represents the discrete time frequencies. As the continuous time frequency is varied from minus infinity to plus infinity, you can see the discrete time frequency is limited to pi and minus pi, or 1 upon 2 to minus 1 upon 2. When the frequency of continuous time signal is between minus f of s upon 2 to f of s upon 2, you can see the discrete time frequency variable is increasing linearly with the continuous time variable, as long as the continuous time frequencies are between minus f of s upon 2 to f of s upon 2, and outside this interval the frequencies are repeating itself. Although in continuous time these frequencies are different, but in discrete time they appear to be same, they are repeating themselves. This effect is called aliasing effect. Therefore, what we do, we usually limit frequencies in discrete time between pi to minus pi in order to avoid aliasing. And these corner frequencies after which the aliasing occurs are called folding frequency. In order to explain it further, let us consider two sinusoidal signals, x1 and x2. x1 has the frequency 10 Hz and x2 has the frequency 50 Hz. Now let us sample both signals at 40 Hz. Obviously 40 Hz sampling rate is suitable for x1 but it's not suitable for x2, right? So we know that aliasing would occur particularly for x2 because the folding frequency here, which is equal to f of s upon 2, would be 20 Hz. So 20 Hz is the folding frequency. After 20 Hz all the frequencies would repeat itself. So this 50 Hz frequency would repeat itself. Now let us sample x1 and x2 at 40 Hz. We'll get a discrete time signal cos pi by 2n and cos 5 pi by 2n. Now let us plot these signals and see what. This is the continuous time signal x1 having frequency 10 Hz. This is another continuous time signal x2 having frequency 50 Hz, and these are the corresponding discrete time signals, and you can see they are exactly same. And this is what we expected from the example. So x1 and x2 are aliased at sample rate equal to 40 Hz. Mathematically, we can see 5 pi by 2n can be rewritten in this form. We can rewrite cos 5 pi by 2n in this form, or simplifying it further, we will get this is cos pi by 2n, which is exactly equal to. Now let us choose different sampling frequency, say 410. So now obviously the folding frequency is 410 upon 2, which is 205, and both the frequencies, which are 10 Hz and 50 Hz, are well within the range of folding frequency. Therefore you can see there is no aliasing. Each signal is represented by its continuous time part, right? It's another similar example, and I am leaving this as a homework for you. Try to solve it, and if you have any problem you can ask me later. Now we have a clear idea about the aliasing effect, and we know what is folding frequency. We can better understand the sampling theorem. In order to understand the sampling theorem in a better way, let us consider an analog signal xa of t, which consists of sum of many sinusoids of different amplitude, frequencies and phase angles, and n actually denotes the number of frequency contained in the signal. Many practical signals like audio and video signals are actually of this form over a short period of time. And let's say the maximum frequency component in xa of t is f max, and we know to avoid aliasing the sampling frequency before discussing the sampling theorem, let me introduce you the sync function. In digital signal processing and information theory, the normalized sync function is commonly defined for x not equal to 0 as this, and it is graphically represented in this form. It is a singularity function and it has maximum amplitude at 0 time, and outside 0 range it actually decreases with time. Now sync function has vital importance in digital signal processing when we want to reconstruct the analog signal from the discrete form. Sync interpolation is most commonly used in digital signal processing for converting the discrete time waveform back into the continuous time waveform. Interpolation is basically if you have two data points and you want to find out what is in between, you can use many interpolation methods that are available. Sync interpolation is the most commonly used method in digital signal processing. Now sync interpolation function for reconstructing the xa of t can be rewritten in this form, where 2 pi f max is the frequency of the signal. In order to reconstruct the continuous time waveform from the discrete waveform, sync functions are generated at each sampling interval. These are called shifted sync functions. For example, this one at n minus 2, another sync function, this one at n minus 1t, then another sync function at n plus 1t, another sync function is this one at nt. So different sync functions are generated at each sampling interval, and the amplitude of sync functions are multiplied with the amplitude of the sample, and these all are added together, and once you add all these together, you will get the analog signal reconstructed. This phenomena in detail. In order to consider this example, let us convert this sampled signal into analog form using sync interpolation function. This waveform is basically the discrete version of a triangular waveform. Now, how many samples do we have in this waveform? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. We have 13 samples from 0 to 12. It means we have to generate 13 sync functions. One sync function at 0, then another sync function shifted at 1, delayed by 1 unit, another sync function delayed by 2 units, then 3 units, 4, 5, up to 12. So generate 13 sync functions. In order to generate the sync functions for each sample, we can write this mathematical equation, which is g of t equal to t minus n upon fs, and now we have a sync function at 0, then 1, then 2, 3, 4, up to 12. Now we have 13 sync functions. Now each sync function now will be multiplied with the amplitude of the sample. So sample occurring at 0 as 0 value, at 1 whatever the value is, it's multiplied with the sync function, then similarly here, 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 and here. Now we have multiplied shifted sync functions with the amplitude of the sample at each sampling interval. Now what we have to do is we have to add all these sync functions together. All these sync functions together, you will get this analog signal reconstructed from the sampled form. Obviously it is not very accurate because we have not enough samples to reconstruct the actual waveform. If we increase the number of samples per unit time, we may have better example. Here in this figure you can see we have now twice as much samples per unit time, and the reconstruction of the signal is much better as compared to this one. Now we can state the sampling theorem in a better way. The sampling theorem guarantees that analog signal can be perfectly recovered as long as the sampling rate is at least twice as large as the highest frequency component of the analog signal to be sampled. Mathematically, f of s, the sampling rate, should be greater than twice the maximum frequency component. And what happens if we do not sample the signal with sampling frequency greater than the twice of the maximum frequency? Aliasing will occur, and aliasing means higher frequency signal components would be represented by low frequency signals. And you know better what aliasing is. We have discussed it in previous slide. There are many types of sampling. Critical sampling, in which f of s is equal to twice the maximum frequency. This is called the Nyquist rate. This is also called Nyquist rate. Undersampling, when sampling frequency is less than the twice maximum frequency. Obviously, when you undersample any continuous time signal, then the aliasing effect will occur. Oversampling is keeping the sampling frequency much greater than the twice of the maximum frequency. Let us consider this very simple example in which we are given a continuous time signal 3 cos 100 pi t, and we have to determine the minimum sampling rate to avoid aliasing. And in part B, if the signal is sampled at the rate 200 Hz, what would be the discrete time signal? So solving part A first, the frequency of the continuous time signal is 50 Hz. So the minimum sampling rate required to avoid aliasing would be twice of the 50 Hz, which is 100 Hz. Now part B, if the signal is sampled at fs equal to 200 Hz, then the discrete time signal would be obtained 100 pi upon 200, which is 3 cos pi by 2n. Another similar example which I am leaving as a homework for you. Now let's move on to the next example, a slightly more complicated example. In this example, we have an analog signal which consists of 3 different frequency components. This one having frequency 25 Hz, this component has the frequency 150 Hz, and this has the frequency component 50 Hz. What is the Nyquist rate for this signal? Obviously, the Nyquist rate is determined from the highest frequency component of the signal. This signal has 3 different frequency components: f1 25 Hz for this component, f2 150 Hz for this component, and f3 50 Hz for this component. So highest frequency component f max is 150 Hz. Therefore, the Nyquist rate would be determined from the maximum frequency, which is twice the maximum frequency, and it is equal to the discrete time signal of 300 Hz by sampling at Nyquist rate is this one. And simplifying it further, you will get this equation, and in this equation you can see this component is sampled at 0 crossings, and it won't appear in the discrete time version, although it is a signal of the highest frequency in the analog version. But in the discrete version it would be 0. In order to avoid this, we must follow another similar example, the sampling frequency in which we have 3 the maximum frequency components. We have to determine what is the Nyquist of the signal. In part B, assume now that we sample this signal using sample rate 5000 samples per second. What would be the discrete time signal obtained, and what is the analog signal that can be reconstructed with the samples if we use idea interpolation? So this is example. Also, I'm leaving this as a homework for you. It is exactly same as the previous example, and that is end of this lecture. If you have any questions and queries, you can contact me using the email address given on the first page. Thank you very much.